Studio Ward is about exploring fashion, innovation, and craftsmanship, working with dead stock materials, upcycling garments and textiles, and using efficient techniques are a part of how my brand is making better clothing. Recently, I got the chance to work with Deakin University and Dr. Fatemeh Mokhtari on using a new technology that has the potential to radically change the way we design and wear clothing. Combining fashion, technology, and sustainability, let's explore the piezoelectric fabrics that are turning wasted energy into power. As more electronics are incorporated into garments, smart textiles will help keep our clothing flexible, lightweight, and comfortable to wear. Many current examples of wearable technologies are powered by batteries that are rigid and require replacement or recharging. Powering these devices and sensors with discrete forms of electrical generation can help to do away with the more clunky parts of circuits. Researchers are exploring various technologies that can more seamlessly produce electricity in clothing. Among these technologies are solar power, triboelectrification, and piezoelectrification, which is the focus of this video. So the piezoelectric effect refers to the special ability of some materials like ceramics, crystals, and biological matter to generate an electric charge through mechanical stress. Actions like tapping, bending, pulling, or otherwise deforming these materials can produce a voltage. Combining these piezoelectric materials with conductive materials or electrodes creates a generator that can be used within circuits. In her research, Dr. Mokhtari developed woven, knitted, and braided textiles to convert mechanical energy into electricity. What I found particularly interesting was the braided piezoelectric generator she made. How it works is that it combines piezoelectric materials with electrodes to make a generator that can be easily included in clothing. It has an inner electrode made from a nylon yarn that has been coated with silver, making it conductive. Around the yarn, a polymer of polyvinylidene fluoride, PVDF, is melt spun and braided. The polymer has a barium-tight knit addition to enhance its piezoelectric performance. Finally, the same nylon silver yarn is braided around the piezoelectric material to form an outer electrode. This structure is important to the function of the braid because the piezoelectric layer functions as both the generator and the insulator that separates the inner and outer electrodes, keeping them from short-circuiting. The opportunities behind piezoelectric technologies in smart textiles and fashion are huge. Especially important is the innovation behind the melt spinning of the piezoelectric components of the braid. This is a big step toward making e-textiles more simple to mass produce and bringing a sustainable and convenient technology to market. The natural motion of the human body offers key points where piezoelectric generators could be deployed to harvest mechanical energy. Through fashion design, smart textile technologies can be effectively united with the human body. The elbows, knees, groin, armpits, hands, feet have great range of motion and receive or place pressure on the surfaces they come in contact with. Optimized designs will focus on these key zones to maximize performance of embedded piezoelectric components. Supplied with a limited amount of the piezoelectric braid, I experimented with how it could be incorporated within garments and chose to produce a glove prototype to demonstrate its capability. The main advantage to including piezoelectric materials in gloves is that our hands are constantly engaging with other surfaces and materials. Grabbing objects, flexing fingers, and clapping are all ways that energy can be harvested. In this sketch, I zoom in on the components required to construct a usable device powered through piezoelectric generation. A rectifier and capacitor will help to create a stable flow of electricity for a connected sensor or other device. Here you can see me testing the signals produced by a small component of the braid. Even with minimal movement, the braid is sensitive enough to generate a voltage. Embedding more braids in the design will further increase voltage output. By attaching the braids to the flanks of the glove's fingers, I can maximize energy production while minimizing their impact on the flexibility and comfort of the wearer. Through this prototype, I have developed some general principles that could support the integration of piezoelectric braids in other designs. Different design problems will dictate the amount and application of the technology within the garment. As an example, energy production considerations in activewear will be completely unique from those in high fashion. Athletes and fitness enthusiasts are interested in tracking and accessing data using wearable technologies. The opportunity for piezoelectric components in activewear is in integrating with biometric sensors for measuring pace, steps, heart rate, or force of impact. Using new technologies and the finest craftsmanship, high fashion offers an opportunity to elevate the piezoelectric braid to an iconic fashion motif. Contributing to a texture, color palette, or silhouette, the use of this technology in high fashion will influence the way people see, think, and feel about energy production in clothing. As development of smart textiles continues to progress, fashion designers have an opportunity to contribute their expertise in collaboration with researchers on better technologies, turning smart textiles into smart fashion.